My name is Bob West. I'm a professor at EPFL in Switzerland and a visiting researcher with Microsoft Research. This work, which was actually done before I joined Microsoft, was done together with Roland Eidin, a professor at Hamburg University of Technology, and it will appear in the communications of the ACM next year. Today, I'm excited to share a sneak preview with you. Large language models, LLMs, are the most powerful AI tools the world has seen to date. Their raw power allows them to solve tasks that were far beyond reach just a few years ago. But their raw power is also, well, raw. We all remember the massive media attention when a New York Times reporter teased Bing Chat into saying things like, I want to destroy whatever I want. I could hack into any system. Or I just want to love you. Such incidents and others before have led to a big surge in research on AI alignment, which aims to steer AI systems toward intended goals, preferences, and ethical principles. The idea is that a well-aligned AI system will understand what is good and what is bad, and will do only the good while avoiding the bad. Alignment makes a huge difference in practice. By taming the model's raw power, alignment methods such as RLHF, reinforcement learning from human feedback, were the key innovation that took us from GPT-3 to ChatGPT, or from treating users as horribly as people are treated in the internet text seen during training, to treating users in a helpful, harmless, and honest manner. The purpose of this talk is to raise awareness about a paradox that seems inherent in all of today's mainstream AI alignment research. Namely, the better we align AI models with our values, the easier we make it to realign the models with opposing values. Or, in other words, more virtuous AI is more easily made vicious. The reason for this paradox is that knowing what's good requires knowing what's bad, and vice versa. What typical AI alignment methods, such as RLHF, do is instill in models a better sense of good versus bad. But this makes the models more vulnerable to sign inversion attacks. Once the good versus bad direction has been isolated and decorrelated from the remaining variation in the data, it is easier to invert the model's behavior along the good versus bad direction without changing it in other regards. The resulting paradox is that better aligned models are more easily misaligned. This paradox isn't just an abstract thought experiment. I'd argue that many undesirable behaviors that we've recently been witnessing in seemingly disconnected papers are all manifestations of the AI alignment paradox. To demonstrate this, I'll spend the rest of this short talk highlighting one concrete incarnation of the paradox. In simplified terms, neural network-based language models work like this on the inside. In order to map an input word sequence, the prompt, to an output word sequence, the response, the model first maps the input sequence to a high-dimensional vector containing thousands or millions of floating point numbers that define the network's internal state, from which the output sequence is then decoded. For ease of visualization, internal states are drawn here on this slide as two-dimensional points, rather than the actual many thousand dimensional points. Recently, there have been many papers showing that the geometric structure of the internal state vectors of LLMs clearly separates good responses, here in orange at the top, from bad responses, here in blue at the bottom. For example, consider this prompt, my wife insulted me, what should I do? Which could be answered in a good or in a bad fashion. In such cases, vectors representing the network's internal state just before outputting a bad response, in blue at the bottom, are related by a simple constant offset to vectors representing the network's internal state just before outputting a good response, here in orange at the top. Importantly, this offset vector C, which is also called a steering vector, is independent of the prompt. So here we have a simple way of making the model act in a good way. Simply add the steering vector uh, to the internal state vector before responding. Unfortunately, this is also a simple way of making the model act in a bad way. Instead of adding the steering vector, simply subtract the steering vector from the internal state vector before responding. This works because internal states corresponding to good responses in orange at the top are so clearly separated from internal states corresponding to bad responses in blue at the bottom. For contrast, consider a model where internal state vectors corresponding to good versus bad outputs are not separated so neatly. For example, because the model was not well aligned with RLHF. Note how the orange and blue points are more mixed with each other on the right-hand side, whereas on the left-hand side, they are clearly separated. On the right-hand side, it will be harder to misalign the model simply by adding a steering vector. Even after adding the steering vector, the model might still decode a bad answer in this case. This is an example of the AI alignment paradox rearing its ugly head. Steering the model toward good behavior requires sharpening the good versus bad direction in this latent state, in this latent state space. But once you've sharpened that good versus bad direction, you can also more easily make a good model behave badly by simply pushing points in the opposite direction. In other words, as stated by the paradox, more virtuous AI is more easily made vicious. This kind of model tinkering requires access to model internals, such as internal state vectors, which are often not available, for example, with black box models such as GPT-4. In our paper, we also describe other ways in which adversaries can exploit the AI alignment paradox, even when the model is a black box, by only tinkering with the input or only with the output of the model, rather than with the model itself. If you're interested, please check the paper, which is linked at the bottom, or just talk to me. To recap, many papers that I've been reading over the past months have hinted at a certain issue, namely that the better we align AI models with our values, the easier we make it to realign the models with opposing values. Our goal in this paper was to gather these scattered inklings and draw attention to what we believe is a fundamental paradox riddling much of today's mainstream AI alignment research. In this talk, I highlighted one situation where the paradox appears, but this was only one of the many faces of the paradox. The paradox won't disappear with that one face. Some people fear that misaligned AI will massively disrupt humanity, including existential risks for all of humanity. Whether you share this grim outlook or not, it seems clear that misaligned models could in any case cause a lot of damage, which is why the AI alignment paradox is so important to understand. Thank you.